Since I was able to finish the lecture last Wednesday on this chapter, that leaves us a buffer day that I would normally use to finish out the introduction of the material, which frequently happens in a face-to-face environment. But in this environment, things seem to go a little quicker. So we've got this buffer day, and rather than jump into the review document and use it as our base of operation, I'm going to go into Cengage Homework and pick out some of those homework problems, and we'll talk about those. And in order to do that, of course, I need to share and find out where I put it. Here it is. There we go. So now we've got, this is what Cengage Homework looks like to me as an instructor, where I can pick out the questions, and these are all the questions that I've got for you to do as your homework, but there are a whole bunch of others left over. And I'm going to dig into the leftovers, and we're going to start at difficulty level 1 and do a few of those until we start to see repeats, repetition of material, and then we'll move up to higher levels of difficulty. So let's just pick out this first one. I think it's already set. Yep. And I'm going to scroll up some so we can get more of the bottom of the frame available. Okay. Start off really simple. For this problem, an FM station, radio station, broadcasts at 95.1 megahertz. Let's see, I wonder if it'd be useful to put 07046. So that's the problem we're working on. So we're given this frequency. Megahertz is a frequency, not a wavelength. Okay. And they want us to calculate the wavelength of the corresponding radio waves. It's useful to look at the answer units, so we know whether they're expecting wavelength in meters. Okay, so we got megahertz to start with, and we know that the conversion of wavelength to frequency follows this formula. Yeah, I can do better than that. There. Wavelength times frequency equals the speed of light. And these units are determined by the value of C. C is a constant. My mind's gone blank. All right, I think it's 2.9979. But to save myself some trouble, I'm going to look it up. Must be the weather. Yeah. This is 2.9979 times 10 to the 8th meters per second. So that means the wavelength has to be in meters, and the frequency has to be in reciprocal seconds, or hertz. Hertz would be the equivalent to that. Well, we're going to solve for the wavelength, but our frequency is in the wrong units. This is megahertz. So what's mega? Mega is 1,000,000 times. So the easiest way I found to convert this unit to another unit is take this mega. What does it mean? Well, it's 95.1 10 to the 6th is a mega, and then hertz. Okay, so we just put this thing right here, right there. Okay, and since your calculator doesn't care whether it's in scientific notation, just exponential is good enough. Or we could convert it, right? Convert this to scientific notation, just move the decimal over one more, store that 10 over here. 9.51 times 10 to the 7th hertz, which is the same thing as reciprocal seconds, cycles per second. Now we'll solve for that. So we just divide this by that number. (9.51 exponent 7) divide. So I get 3.15 meters. Okay. Now let's see if Cengage likes my answer. Indeed it does. Okay, that was a fairly simple one, and it's good to start off simple. All right, let's be sure we stay on screen there. Okay, the next one, let's find another number one. Here we go. How about this one? Let's see if this gives us something new to work on. Okay. Let's see. What are our answer choices? Yes, no. Yes, no. Okay. So this is 7069. What information are we given? Well, let's just read the whole thing through, and then we'll decide. Question and information given. Does a photon of visible light, wavelength between 400 and 700 nanometers, have sufficient energy to excite an electron in a hydrogen atom from the n equals 1 to the n equals 5 energy state? And then the second question is, does it have enough energy to go from N2 to N6? All right. So the question is, we're focusing on energy. Right. Energy. Is there sufficient energy to excite an electron in a hydrogen atom from n equals 1, that's initial, to final, n equals 5 energy state? And these are visible photons, so between 400 and 700 nanometers. All right, what's a nanometer? A nanometer is 10 to the minus 9th of something. So if we take 10 to the minus 9th here, we could say it goes from 400 to 700 times 10 to the minus 9th meters. Or take these two, subtract from that one, I'll actually add it to that one. Between 4 and 7 times 10 to the minus 7th meters wavelength. Okay, let's try to make this easier on ourselves. Which end of this spectrum has the lowest amount of energy? The longer wavelength has the less energy, right? As the wavelength gets bigger, frequency gets smaller. And as frequency gets smaller, energy gets smaller. All right, so actually I'm approaching this the wrong direction. we should look at it in terms of how much energy is required to go from 1 to 5. That would be a better approach. So what is the formula for that? Well, it's in your review document. And on the useful information page, let's see if I can find it. Yes. So the change in energy required here, and that's what we're looking for. Because this electron is at an energy state relative to the nucleus, actually relative to infinity. And this one is at a different energy state. So what we need is the energy for level 5 minus the energy for level 1. That difference in energy is what has to be supplied by the photon. Okay. Well, each one of these has a formula for it. So this one will be minus 2.178 times 10 to the minus 18 times Z. What is Z? Z is the same thing it's always been. It's the atomic number. For hydrogen, it's 1. So Z squared is 1 divided by N squared, 5 squared. Then we subtract times 1 again, and this is 1 squared. Okay? Now, if you want to, you can factor out a term. You can factor this one out to the outside, and then do that operation on this one. Or you can do it just like this. Just say this factor minus that factor. By the way, what are the units of energy here? They're SI units, joules. Okay? So let's do that calculation. Let's say 1 divided by what? 25, 5 squared. Times this number, 2.178, change the sign, exponent 18, change the sign. So I'm going to write these down as we go. This value is minus 8.712 times 10 to the minus 20 joules. So that's the energy for the electron when it rises to the 5th energy level. What is it before it rises? That's what this term is. Oh, that's times 1, duh. There we go. So what's the difference in energy? This is the amount of energy that has to be added to the atom. Right? So I would expect the value to be positive, would you not? So let's take this one. Let me see. Hold on a second. Where am I? Whoops. Left out that negative sign. So this is going to be a positive term here. So the change in energy is equal to a positive 2.091 times 10 to the minus 18 joules. Okay, that's the amount of energy required to raise an electron from 1 to 5. Okay, so now how do we figure out what the relationship is between that and the wavelength? Well, we need another formula, right? Remember, energy equals Planck's constant times frequency. Well, we don't have frequency here. We have wavelength. So let's put in the equivalent of wavelength, which is what? Well, I erased it. Right? If C equals wavelength times frequency, then frequency equals C divided by wavelength. Okay? So, let's, I need some space. Maybe I can put it over here. See, yeah, I'm still on camera. So Planck's constant, what is that? All right, it's also in useful information. Planck's constant is, I have to find it. Here it is. 6.626 times 10 to the minus 34. Minus 34 joules seconds. And that's times 2.9979 times 10 to the 8th meters per second divided by the wavelength. Well, we don't know what the wavelength is yet, but we do know what the energy is. The energy is 2.091 times 10 to the minus 18 joules. Okay, now we have an equation in one unknown. So how do we solve this equation? Let's see, this is equal to that times that. So if we bring this term over here and put this term over there, we have 2.9979 exponent 8, and then we're going to divide it by this term that came from here. There it is, right there. And then multiply it by Planck's constant. So I get 9.50 times 10 to the minus 8 to the minus 8 meters. Okay? So how many nanometers is that? Or we could just compare it to these meters. 10 to the minus 7th meters. This is a much shorter wavelength. So I would say, yeah, it does have enough energy because shorter wavelength means more energy. So it has abundance of energy. Now, will it happen? That's another question. It has enough energy, but that electron's not going to move unless the wavelength of light exactly matches the energy it needs. That's because these levels are quantized. Nothing moves between them unless there's an exact match in wavelength and energy required. But to answer this question. We just say, yeah, there's enough energy there. Doesn't mean it's going to happen, right? So I would say, unless my reasoning is completely wet. Oh, we got to do the next one also. All right, so 2 to 6 would be here. Okay. 2. And this is 6. There we go. Now, final is 6. And initial is 2. Okay. You know what? I think I'm reading this backwards. What were we calculating here? We were calculating the amount of energy required for the electron to be promoted. That's how much is required. Right? That wavelength would give us enough energy required. But this is a longer wavelength, lesser energy. So my answer is backwards. It should be no. There's not enough energy. That wavelength, any of those wavelengths is too long, which means not enough energy. Right? What else do we know? We also know for the second half that between 2 and 6 is a smaller jump than 1 to 5. Why? Because remember when we looked at the representation of energy levels, 1 to 2 to 3 to 4, you know, the higher they got, the closer they were together. So the second one, it could possibly have enough energy. So let's do this calculation and see. This is 6 squared. Okay. So let's make room here. You know, I want to take another approach. Now, this is the right approach. Sorry, I'm thinking out loud. I did it right the first time because we've got a range of energies here, and to use my other approach, I'd have to calculate the energy for that one and for that one, and then see if this energy matches. This way, we only have to do this calculation and that calculation. So let's continue to do it that way. All right, how much energy is required for this promotion? We need to resolve that formula. Okay, so this would be okay. 36 divided into that number. There we go. And let's see. And then 4 divided into that number. Okay, but this is now positive. And then I need to add those two together. 4.84 times 10 to the minus 19 joules. And that's a positive number because we're adding energy into the system, and the atom is the system. So now this one is equal to that. There we go. Okay, so now I need to bring the wavelength over here, and I need to say this number divided by that number. And then times that number. Planck's constant. So I get 4.10 times 10 to the minus 7. Meters. Okay. It looks to me like we do have enough, because this falls within that range, right? 4 to 7, 4.1. So the second one should be yes. First one's no, second one's yes. Okay. And that looks like the same way that they did it. The energy of the photon required here and then here, two different values, and then convert those into wavelength. Okay, any questions? Besides, why did it take me so long to get it done? All right, so let's see if we can find another number one. Here's one. Let's see how it compares. Arrange the following groups of atoms in order of increasing first ionization energy. Okay, now we're going to periodicity. I'll leave that open. We might need that table again. Okay. 7.111. It'd be better if I had a periodic table up here, but I can only share one thing at one time. So I might have to use my periodic table here. Okay, calcium, strontium, cesium. Where are they? Calcium's right here. Strontium's right here. And cesium is over here. So if they're in order, increasing first ionization energy, right? So what's the trend? Ionization energy, first ionization energy, increases from left to right across a period and from bottom to top in a group. So from lower left to upper right, we should see an increase in first ionization energy. So cesium to strontium to calcium should be the order. And they want us to put those in order. Cesium, separated by commas, strontium, and calcium. Okay. How about the next one? Neon, phosphorus, and calcium. All right. Neon's way over here, upper right-hand corner. Phosphorus is right here to the left. Calcium is over here. Calcium would be the lowest. Phosphorus will be the next. Neon will be the last. So we'll put in calcium, and then phosphorus, and then neon. Okay? Then we'll go to the last one. Cobalt, sulfur, and oxygen. Cobalt's here. Sulfur is here, and oxygen's above it. that was nice of them to put cobalt way over here by itself, because the transition metals tend to be a little squirrely with these trends. So putting cobalt way over here and the other choices over there separates them sufficiently so that cobalt is going to be the lowest, then sulfur, and then oxygen, because oxygen's above sulfur. So cobalt, sulfur, oxygen. Now, as given. Let's see. Now, the only thing it says, comma separated list, right? I didn't put any spaces in there, so I assume that we don't need them. Let's see if we do. Oh, it liked the answers. All right. Let's look for another number one. Scroll up just a little bit so I can see what I'm doing. Oh, there's one right below it. Now we're starting to get repetitious here. Let's move down some. Wait a minute. What was that one? Was that radius? Ah, increasing size. Excuse me. My mistake. This is different. It's a different trend. So what is the trend for atomic size? Right? They get bigger going down, correct? Smaller going up, and smaller to the right. Right? So they get smaller this way and smaller that way. So atomic size is a similar trend to first ionization energy. Let's see if that makes sense. Okay, if you're going from left to right, what are you doing? You're adding protons, but you're not adding electrons in a shielding position that can sort of protect the outer electrons from the attraction from the nucleus. So that means that nucleus has full effect on the added electrons. So as you add electrons from left to right, you're also adding protons and you're shrinking the atom. So the size gets smaller from left to right. When you're going down, you're adding energy levels, which is just big, 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 bigger, 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 bigger. And the inner core electrons are shielding the outer ones from those added protons in the nucleus. So they get bigger going down. So that means they get smaller going up. So lower left, upper right, the atomic radius, atomic size decreases. All right, so now let's look at the questions. Sodium, potassium, magnesium. Okay, here's sodium, potassium, there's magnesium. So we would go potassium, sodium, magnesium. Backwards. Well, no, not backwards. Just in that order. Potassium, sodium, magnesium. There we go. Got that one done. How about barium, germanium, argon? Let's see, where's barium? Barium's way over here. It's a big one. The next one, germanium, is over here, right? It'll be smaller. And then argon to the right should be even smaller. So barium, germanium, argon. There we go. And last, nitrogen's here. Right. There we go. Nitrogen. Barium's way over here, so it's the biggest one. And germanium again. So barium, germanium, nitrogen. wonder, when you get to argon, now this is an increasing size. I'm doing it backwards, are I not? Yeah, I'm doing it backwards. Increasing size would be the other way around. Potassium, sodium, magnesium goes the wrong direction. So I got to reverse them. I got to put magnesium over here. There we go. And then I'm going to reverse this one. So my question is, argon's a noble gas. It should follow that trend. So argon's going to be the smallest one. Barium will be the biggest one. There we go. And then we need to put nitrogen over here. And barium back on that other side. Now they're in the order that the question asks for, increasing size. Okay? It helps to reread the question occasionally. So we've done ionization energy, size. Now I want to look at, see, what is this one? Okay, this question asks about, I didn't put the number up there for that one. This is 7115. This question asks about ion size. In general, we only discussed ions in terms of well, the ion size related to the atomic size. So let's see if we can make sense of this. Maybe I can, maybe I can't. Which atom or ion has the smallest radius? Okay, let's see where we're dealing with here. Tellurium. Tellurium's over here. Right? So it'd be a fairly large atom. Selenium is here, and sulfur is there. Right? So each one of these, when they ionize, their most common ion is going to be an addition of 2 electrons. Right? So if you add 2 electrons to each one is going to get bigger. So the sulfur should still be the smallest one, simply because you're adding electrons makes it bigger, but you're adding electrons to a lower energy level for sulfur. Hello? Okay, so I would expect sulfur to be the smallest radius ion here. How about cesium, germanium, argon? There's cesium, there's germanium, and there's argon. Now the size of each neutral atom would be smallest for argon. But what happens when you add an electron to argon? There's no place for it to go in the 3rd period. It has to jump to the 4th period to accept that electron. Well, actually, it doesn't say whether you add an electron or you subtract an electron. Right? If you subtract an electron, then it'll get smaller. If you add one, it'll get bigger. So let's see, germanium and cesium. Well, this may be a moot point. If you add an electron, actually cesium, you're going to subtract an electron simply because it's a metal. So it's going to get smaller. Right? But is it small enough? Germanium's up here a couple levels above it. And argon would either be add an electron to go from there or subtract an electron to go from here. So I still think argon is going to be the smallest one, no matter what you do to it. Well, let's see if I'm right. Yeah? Now, I'm interested in the reasoning here. Atomic radii decrease in going from left to right across period. Okay, that talks about atomic radii. When comparing the same element with a differing number of electrons, look at the atom or ion that has the fewest number of electrons because it has the smallest number of electron repulsions. Now, we didn't cover that, so I wouldn't expect you to know that one. My reasoning got me the right answer, but it's not the same reasoning that they were using. Now, what do they mean by the fewest number of electrons? They can't mean the total number of electrons. They must mean the fewest valence electrons. Okay, let's move on. All right, this looks interesting. Arrange the following atoms in the order of increasing ionization energy by numbering them from 1 to 4. Okay, we've done one like this. We're already here. We might as well do it. 07120. Okay, if we're going from lowest ionization energy to 4 highest. So which would be the lowest? Well, let's see. Where are they located? Silicon is way over here. Carbon is above it. Right? It would have a higher ionization energy. Germanium is down below, and indium is over here. So indium would have the least, be number 1. And the other 3 are in the same family to the right of indium. So they would go to 2, 3, 4. Because carbon would have the highest ionization energy out of that group. All right. Let's see. That was number 1. There's another number 1. Largest atomic radius. Oh, electron affinity. Okay, we've got electron affinity here that we haven't discussed yet. So let's take this one just so we can get at that problem. Okay, let's see. Compare these elements. Which element has the largest atomic radius? The largest atomic radius would be the one to the below and to the left. So there's sodium, and boron's to the right of sodium and above it. Aluminum's to the right of sodium. Sodium still wins. Carbon. It looks to me like sodium would have the largest atomic radius. It's far to the left of the rest of them. Okay, which element has the largest electron affinity? Now, here's the question that I have to ask. Electron affinity, let's go back to the definition. Let's see, am I on the right one? No, we're on a different one, 124. Electron affinity takes the ground state atom in the gaseous state and adds an electron to it. Right? So, where does the energy go? Well, if this is attracted to that, and that is a lower energy state here, then it must give up energy. In other words, the delta H is going to be negative. Okay? And the more negative, the stronger the attraction of the electron for that ground state atom. Okay, so when they say which one has the largest electron affinity, my question is, are they taking that negative sign into account? They should be. The larger value, the larger value would be more positive, which means you want the one with the least electron affinity. And in order to get that, we need to be, the greatest electron affinity is up and to the right. Right, up and to the right. So the more negative is up and to the right, so the more positive is down and to the left. So down and to the left here would be boron, aluminum, down to the left would be sodium. Sodium also. Now, I could be wrong if I interpreted that wrong. If they're saying largest, maybe they mean largest absolute number, in which case it'd be just the opposite, it'd be carbon. But I'm going to leave it there and just see what happens. What element is expected to have the largest ionization energy? Okay, so this one is fairly simple. Largest ionization energy is up and to the right, which means carbon out of those four. Now let's see what we get. Well, let's see if I missed the one that I thought I was going to. Atomic radius increases from right to left and top to bottom. Boron has a larger atomic radius than carbon, aluminum larger, and sodium has the largest atomic radius. So that one's right. Electron affinity, that's the one that we messed up, or I messed up. Carbon has the largest electron affinity, which means it has the most negative of the numbers. See, that's a matter of interpretation. So technically I got it right. Let's move on. There's a one. Let's see if it's something new. The successive ionization energies for an unknown element are 896, 1752, 14807, 17948 kilojoules per mole. To which family, that is, which group in the periodic table does the unknown element most likely belong? All right, so here's a test of whether you remember the difference between ionization energies for valence electrons versus core electrons. That's 159, 07, 159. So the first ionization energy does what? Removes one electron, and that's going to have a delta H, some value. They use I, so let's be consistent. They're calling it I. 1. Second ionization energy is this one. And that one has there. Okay. third ionization energy takes this one, and you lose another one. Okay. That's as far as we need to go for this one. Notice, first ionization energy is here. Second one is larger, right? We would expect that. The third one is huge compared to the second one. That means that most likely these two electrons are valence. And this one is core. So which group in the periodic table has available two electrons, two valence electrons, and the third one is in the core? The second group, the alkali metal, the alkaline earths, this group. Right? For example, if we took magnesium, remove one electron, that puts it here. Remove another electron, that puts it over here. The third electron is like trying to strip an electron from a noble gas. So this would be alkaline earths. Okay? All right. We're approaching 3 o'clock, and let's see. We're good till 3:45. So I better kick it up a notch here. Let's see if we got any more ones that give us something new to deal with. Doesn't look like. Oh, there's one. Okay, this one, rank the following atoms and ions from least to greatest ionization energy. This is kind of a takeoff on the one we just did. Right? This is, oh, this one doesn't have a number. This was Chem work. Right? Okay, so rank them from least to greatest ionization energy. Okay, notice we're starting with well, we got a noble gas in there and the others are ions. So I have a sneaking suspicion that those might be isoelectronic. Let's see. There's krypton, right? It has an electronic structure. If we add an electron to that, we get bromine. No, they're not isoelectronic. Oh, wait a minute. No, they are. They are. Excuse me. Bromine has 35 electrons. Krypton has 36. Add an electron to bromine, you get a krypton. Electronic structure. Okay, so those are electronic. Those are isoelectronic. How about rubidium? Rubidium's here. If you subtract one, you go from 37 to 36. Okay. Strontium, you're going from 38 to 36. Okay, so those are isoelectronic. This is an isoelectronic series. But that means that if we remove an electron, let's see. The question is, are we removing electrons from the core, or are we removing them from a valence electron? Well, bromine has how many valence electrons? It actually has 7, right? 7, 6, 5, 4, 3, 2, 1. And we've added an extra one. So that electron will be easily removed. So bromine would be the would have the least ionization energy right here. Okay, what would have the greatest ionization energy. Well, each one of these, rubidium here, has already lost one, so now you're going to get into the core. Strontium lost another one. You're going to get into that core. So the key here is how many protons are there holding those core electrons in place? Because strontium, rubidium, and krypton are all isoelectronic at the same energy level, right? Krypton is N equals 4. So it's not just the core electrons that we consider, but how many protons are there holding them together. So the most energy will be required to removal of a core electron with the highest number of protons, which would be strontium. So strontium should be the highest. And the next one should be rubidium. And this middle one should be krypton. That's my reasoning. Let's see if it works. Uh-oh. Did I do them backwards? Ionization energy. It didn't like that at all. Please try again. I think my reasoning was sound. Try another version. Show hints. See where I went wrong. They have the same number of electrons. That's true. Yes. How about hint 2? Since this is an isoelectronic series, the number of will determine the size of the atom. I don't get it. I don't see where I went wrong. The ionization energy should be increasing from lower left to upper right.
I think it wants you to enter the letter that corresponds with the element. The A, B, C.
Oh, thank you.
Yes.
Okay. All right. Well, it's not going to let me do this one over again, so I'm going to have to start. Try another version. Okay. So let's see here. Oh, we do have an anion here. That would be the least one. D. Okay. And the greatest one would be strontium, which would be C. And the next one would be rubidium, which would be B. And krypton, which would be A. Yay! You guys have more experience with this homework than I do. I just put the thing together and then let it run. But you've had a chance.
It can be tricky sometimes. They throw things in there.
Yeah. I don't know why they call them expert systems, because they really are stupid. Okay, enough of that. Let's see. That was probably that's the last number 1. So let's go back up and look at some number 2s. And if we get through the 2s, I think we'll be okay. The 3s start to get a little really difficult. So let's see what the 2 has to say. Carbon absorbs energy at a wavelength of 150 nanometers. Okay. The total amount of energy emitted by a carbon sample is 1 times 10 to the 5th joules. Calculate the number of carbon atoms present in the sample, assuming that each atom emits 1 photon. Okay, so this is a combination between energy equivalence, wavelength equivalence, and dimensional analysis. Okay. So let's see, we're at 053. 07. 053. All right. So what are we given? We're given carbon absorbs at 150 nanometers. So the wavelength equals 150 nanometers. And the total energy emitted by a carbon sample, the total amount of energy emitted, oh, okay. What they're saying is that once the carbon absorbs all this energy, it re-emits that energy to a total of this amount, 1 times 10 to the 5th joules. So energy here, actually the change in energy, is 1 times 10 to the 5th joules. And we have to assume that each atom emits only 1 photon. So this is per 1 atom. But this is the total. This is per total. Okay. So our equivalence for energy is Planck's constant times frequency, or speed of light divided by wavelength. Okay, so this is going to be here, Planck's constant, speed of light, and this will be now wait a minute. This is not the same as that one. This is total, and this is per atom. Okay, see the difference? This is only calculating how much energy change for 1 atom undergoing that transition. Okay, so this is our unknown. And we need Planck's constant, which is 6.625, was it? 626, 10 to the minus 34. Okay. And then we have speed of light divided by the wavelength. And the wavelength has to be in meters. This is nanometers. So that would be 150 times 10 to the minus 9 meters. Right? I just took that minus that nano and put it right down here. And this will be in terms of joules. Right? Planck's constant, joule seconds, meters per second, meters, cancel second, leaves us with joules. So this is per atom. 6.626 exponent 34, change sign, and 2.9979 exponent 8 times, and then 150 exponent 9, change the sign, divide. So I get 1.32 times 10 to the minus 18. Joules. There we go. Now this is the total joules. Right? So if this is the total, and this is per atom, then let's see, how am I going to do this so it's reasonable? If this is our starting point, 1.00 times 10 to the 5th joules. And this is per atom. Right? Cancel joules, leaves us with atoms. 1.32 times 10 to the minus 18. That should give us the number of atoms. Was that the question? Total amount of energy, number of carbon atoms. Okay. So let's see, got that one, and then we got this one. Fifth. Flip them over and divide. So I get 7.55 times 10 to the 22nd. Atoms. That's not even a mole. Let's see if it likes that number. I hope I put it in right. 7.55 times. X is not part of a valid. Okay. Oh, I know what it is. There we go. To the 22nd. I used Shift 8 for the asterisk. Gives me powers. Okay, it liked it. All right, let's see. Scooch this back over. All right, we still got time. Let's see. That was a number 2. Let's see what this one looks like. It takes 738 kilojoules of energy to remove 1 mole of electrons from an atom on the surface of magnesium metal. Aha! What are we talking about here? The photoelectric effect. How much energy does it take to remove a single electron from an atom on the surface of solid magnesium? Okay, and then what is the maximum wavelength of light capable of doing this? Because if the wavelength gets too long, there's not enough energy. So we got to have it. We got to have less than that wavelength to have enough energy. So the first step is to find out how much energy is required per atom. And let's see, it takes 738. Let's see, what number is this? 056. Okay, so we're given 738 kilojoules, 738.0 kilojoules per mole. There's a surface. This is magnesium. Yeah, it probably doesn't matter, but I'll put it up there anyway. How much energy does it take to remove a single electron from an atom on the surface of solid magnesium? Okay. If this is, and the answer, notice the answer is in joules. Right? So we want to find out per atom. This is simple dimensional analysis. we need to convert that to joules also. So we'll just stick another term in here. Kilojoules. 1 kilojoule is 1,000 joules. There we go. So that'll give us the amount of energy per atom. Yeah, per atom. 738 times 1,000 divided by Avogadro's number. 1.226 times 10 to the minus 18. 1.226 times 10 to the minus 18 joules. And that's per atom. Let's see. Yeah, 4 significant figures. 1.226, and then our exponent should be like that, and negative 18. Okay, now we want to convert that into wavelength. And remember how to do that. Energy equals Planck's constant, C divided by wavelength. So the wavelength then is going to be, move it over here, and that's hc divided by E. So Planck's constant, 6.626 times 10 to the minus 34, I think. And then the speed of light, 2.9979 times 10 to the 8th meters per second. This is joule seconds. Divided by our energy, 1.226 times 10 to the minus 18th. So that'll give our wavelength in meters. Then we need to convert it to nanometers. So let's do this calculation first. 6.626. I hope that's right. Yep. Exponent 34, change sign. And then speed of light. And divide by 1.226. Exponent 18, change sign. See, 1.62 times 10 to the minus 7. 1.62 times 10 to the minus 7th meters. Okay, what's a nanometer? Nanometer is 10 to the 9th. So, in order to be 10 to the 9th here, right, then we move this 2 to the right. That gives us 10 to the minus 9th. And that means 162 nanometers. Let's see. It liked it. Liked it a lot. Okay. There we go. Now, let's see what else is lurking in the shadows here. Oh, calculate the de Broglie wavelength for each of the following. We're going to have to look up some information for this one. So, first of all, 7059. 7059. What is the de Broglie wavelength? Actually, that's not capital. Broglie. It was French. the de Broglie wavelength is was proposed by this fella, and basically what it does is it equates mass to wavelength. Remember, Einstein equates mass to energy. De Broglie came before Einstein, and he equated mass to wavelength. But it can't be at rest. It has to be moving, right? So that's why this problem says it has to be moving at some velocity. In this case, it's 20% of the speed of light. A tennis ball, in this case, is moving at 45 meters per second. I want to calculate, calculate the wavelength for each one. The equivalent wavelength. So you never thought of yourself as having a wavelength, did you? Well, actually, it's all relative, as Einstein would say. What are you comparing speed of light to? What are you comparing the speed of the tennis ball to? Right? On the surface of the Earth, believe it or not, each one of us is moving at about 1,000 miles an hour. That's because the Earth rotates once in 24 hours, and the circumference of the Earth is about 24,000 miles around. So about 1,000 miles an hour, we're going right now. I mean, not just sitting here. So that's a technicality that we could argue ad infinitum, but we'll just take the problem at face value. Let's see, have I missed somebody? I want to be sure I got everybody down. 5, Amy. Okay, good. All right, so we need some way to equate, to calculate wavelength based on velocity and mass. All right, so I'm gonna ducks in a row here. We can put Einstein and Planck together to give us this wavelength. Einstein said that that's the equivalence of mass and energy. Planck said that energy equals this constant like that. Well, actually, he said it was frequency, but we need wavelength, so I'm going to do it that way. Now, if these two are equal, well, actually, this is the energy of anything traveling at the speed of light. We're going to use a slightly modified version, and that's what de Broglie did. He modified this one to be the energy of that object, and actually we could, yeah, it works. Mass times velocity squared. You know, that's not right. It should be it should be 1/2 mv squared. Shouldn't it? Any object moving has this much energy. So I may come out with the wrong answer. If they're expecting to substitute velocity for speed of light, you know, I think that's what they're doing. For an object moving near the speed of light, its energy is going to be mass times its velocity squared. All right, let's just see what happens. Okay, so when we combine these two, we would say this is equal to that, like that, right? That's equal to that, Those two are equal. Okay, now what are we getting at? We're getting at wavelength. So we need to solve it for wavelength. So let's bring wavelength over on this side, put everything back on the other side. Okay, so we have H, C, M, V squared. Okay, now we can solve the problem for both of them. Just use the same formula. All right, this is going to be 6.626 times 10 to the minus 34. This is going to be 2.9979 times 10 to the 8th. The mass is going to be variable. Electron is going to be really small. Tennis ball, they're giving you the mass of the tennis ball there in grams. And the velocity is going to change. Okay? So these will be variables. Okay, for the first one, what's the mass of an electron? I have to look it up. So I pull out my textbook, and it just so happens, in the back of the textbook, on the inside of the fly, the mass of an electron is 9.10939. Can't even remember what I said. 9.10939 times 10 to the minus 31 kilograms. And then its velocity is 20% of the speed of light. So it's 0.2 times speed of light. And here we have the speed of light up there, right? That's what this is. And then here we have Planck's constant. Okay. So that's the right units, that's the right units, that's the right units, that's the right units. Kilograms. Now, what's the wavelength? Well, they're asking for the wavelength in meters, which is good, because that's exactly what we're going to get. All right, so what is this one? Well, this is 1C divided by 0.1C, so a 0.2C. So 0.2 into 1, what's the reciprocal of 0.2? It's 5, isn't it? Yeah. So we can say 5 times this one. I need to put this in as a constant somewhere so I can just hit one key and bring it up. Divided by this one. So I get 3.44 times 10 to the minus 3 meters. Now, does that seem reasonable? I want to be sure I'm not making a mistake here. that. Okay, I did make a mistake. Forgot to square my value. It just didn't look right. So now, if this one is squared and that one's not, then this one is going to be 0.4, 0.2 squared. And this is going to be times C, and that's going to cancel. And this will cancel. Let me try that again. So let's put in this one. And then divide by that one. Okay. And then square 0.2. Let's see, but there it is. And divide by it. Then divide by the speed of light. Because we still got one speed of light left over. See, it was squared. That one of them canceled, but we still have that other one. Now, 606 times 10 to the minus 11. Meters. That's more like it. And that is actually 606 nanometers. Oh, wait a minute. 10 to the minus 9. No. That's less than a nanometer. A lot less. That is 0.6 angstroms. It's very short. It's shorter than the wavelength of light. That's why they use electrons in electron microscopes, because the diffraction limit for light is at this level. And if you use electrons, you get a diffraction limit way down here, which means you can image much smaller objects. So the electron microscope was invented for that purpose. Okay, so let me put in that number before I erase it. 6.06 exponent. There. Minus 11. There we go. Now let's do the tennis ball. Okay, so the tennis ball, we need a different velocity here. We're going to keep that C. It's not going to cancel this time. And then we're going to square the actual velocity in meters per second, which is 45. Okay. And now we need a different mass as well. So it says it's 55 grams. How many kilograms is that? Well, the simplest way is 55 times 10 to the, how many kilograms is a gram? 1,000th of. There we go. So that's the solution for the next one. Let's see. Let's put in Planck's constant again. 34 negative sign. There we go. Speed of light. Times that. And then let's square 45. And divide that into it. And then divide by this one. 55 exponent 3 change sign. So this is 1.78 times 10 to the minus 27. Meters. So notice the larger objects moving slower have a much smaller wavelength. .78 exponent. Oops, back up, minus 27. Now let's see if I got it right or if I'm just all wet. Oops, I got something wrong. What did I get wrong? Let's see, 20% of the speed of light, okay. Wavelength. Is this the right formula? Okay, the de Broglie equation gives that the wavelength for a particle is h divided by mv. H divided by n. Okay, so I was using the wrong formula. I don't know why this formula didn't work. Oh, probably because that value has to be V also. If that one's V and this one's V, that's it. Then the formula is there we go. Okay. So I was wrong. So it's like this. If we're going to change this to V, that one has to be changed to V also. All right, I needed to crash and burn at least once today. We got probably 10 more minutes. Let's see if we've got one that can be solved rather quickly. Let's try something else. Maximum wavelength light capable of removing an electron from a hydrogen atom from energy, characterized by the following: n equals 2. Now, we've done one like that before. Excited hydrogen atom emits light with a wavelength of 4 to reach the energy level for which n equals 2. Yeah, let's keep going before I run out of time. I may just have to quit. Oh, okay. Here we go. Right, we haven't done any electronic configurations. So this will give us a chance to do a little bit of that work. And this is 085. All right, let's put this back over a little bit. How many orbitals in an atom can have the designation n equals 4? So what we're saying is, remember the principal quantum number, then the angular momentum, then the magnetic, and then the spin. The spin doesn't equate to an orbital, right? Orbitals are just down to here. Spin is just, you can have 2 electrons in an orbital, they have to have opposite spins. So we're talking about how many orbitals can an atom have with the designation n equals 4, right? If n equals 4, how many L's can it have? It can be 0, 1, 2, or 3. You can have 4 levels, right? How about each one of these? Well, that one can have only 1. That's it. This one can have -1, 0, +1. This one can have -2, -1, 0, +1, +2. And 3 can have -3, -2, -1, 0, +1, +2, +3. I might have to take this. Hold on a second. If my wife doesn't get it. I bet she's asleep. Okay, so that's the maximum number. So from all these, we derive this many orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You can have 16 orbitals at that level. Right? And if we look at each one of these, that can have 1, this can have 3, this can have 5, and this can have 7. So that's 12, 13, 14, 15, 16. All right, so let's put 16 in here. And an easy one. If n equals 1, n equals 1, you can only have one orbital. That's the s orbital for n equals 1. Okay? 5 more minutes left. Let's just take one atom and draw its electronic configuration. And then we'll be done. Okay. Okay, if I pick a transition metal, I'm going to pick one that abides by the rules. Okay. I showed you, during our lecture, I showed you, we came across a couple that didn't fit the rules. So I'm going to pick one that does abide by the rules. How about nickel? Nickel has 28 protons, so the neutral atom has 28 electrons. So if we use the periodic table to our advantage, we can fill it in, right? First, n equals 1. You got 2. 1s2. 2. 2s2 takes you to beryllium. And then boron through neon is 2p6. Then we come back down to 3. 3s, 2, 3p6. That goes 3s2, 3p6 all the way to argon. Then we come back over here to 4s2, takes you to calcium. Then we get into transition metals. Now we're back down into Ds, only we're not 4, not n equals 4, n equals 3. So scandium, 3D, and we just count over. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So that's 1, 2, 3, 4, 5, 6, 7, 8. There we go. That's the electronic configuration of neutral nickel. Now, how would we write that shorthand? Well, you go backwards, right? You follow nickel and you go backwards, wrap around until you find the nearest noble gas, argon 18. Right? Sometimes I'll write the number down there. So that means you have 10 more. Where are they going to go? They're going to go here. because this, right, notice there's the octet, that's argon. So we have 4s2, 3, d8. And that's the shorthand version for nickel. Okay. Let's see, Wednesday, I'll pull out the review document that's that you have in Blackboard, and we'll work from that one. I'll pick out some of those and we'll work those. It'll give you a chance to look at some of this stuff, work some more homework problems, and hopefully come back with any questions that you might have. And then we'll do that review on Wednesday, and that means the exam will be the following Monday, a week from today. Actually, you can take it anytime you want to, but that's the deadline. Okay, any questions? Stop the share.